Everyone, my name is Soborno Isaac Berry from Berry Science Lab, and today we're going to be talking about complex analysis. Welcome back to Complex Analysis. Today is lecture number 6, and today we're once again talking about more properties of contour integrals. Okay, so let's review from last time. What is a contour integral? Well, it's kind of an analog to the multivariable line integral, where you take a path, a curve, gamma of t, you draw it out, then you take some surface, you project the curve onto the surface, then you take all of the area under the projected curve, and you find what it is. Alright, so that's essentially how complex line integrals work, except here they give you a real answer. Here they're going to give you a complex answer. So, first question. You probably already know that, where's the marker? You probably already know that over the real numbers, oh wow, that's nice. If you take a surface and then a curve, gamma of t, so f, and then you should know that there are other ways to parameterize a curve that result in the same geometric shape and don't necessarily have the x and y components being the same all the time. For example, take sine t, cosine t, and then take the totally different cosine t, sine t. And both of these, when graphed on the plane, have the exact same graph, even though their respective components are definitely not equal to one another at the same time. There are two different points with sort of a phase shift that trace out the same curve. Now, you can achieve the same effect as well if you just add a multiplier to the time. Now, the point is circling around twice as fast, but the curve that it draws out is still a circle, just the same as the one that's going at 1 times speed. So, these two are the exact same curve. So by the geometric definition of a line integral, they should give the exact same integral. And they do. But does that hold for complex line integrals? Is the integral of f d gamma 1 always equal to the integral of f d gamma 2 if gamma 2 is a reparameterization of gamma 1? Well, the answer, it turns out, is yes. Why? Well, recall that the definition of a line integral f d gamma is f of gamma d gamma, which further expands to f of gamma of t, and you can't integrate that with respect to gamma, so you're instead going to have to do d gamma dt dt. And so you rewrite this as gamma prime of t. That is a line integral over gamma. And whereas this is from a to b, this is more like, say, gamma inverse a, gamma inverse b, or t1 to t2. Now, we haven't actually evaluated a contour integral yet, so let's do that real quick. Let's say we have, I don't know, what's a nice function to integrate? Let's say z squared and we want to integrate it from 0 to 1 plus I, this is the real axis, this is the imaginary axis, along this nice line. First, how do we parameterize that line? Well, we can always parameterize it as gamma of t is equal to t plus it. Or you can also parameterize it as, well, minus 2t minus 2it. Or you could also parameterize this as any number of options. But keep in mind that they're going to take different times to reach 0 and 1 plus I, respectively. If we just choose t plus it for now, how do we calculate this? Well, it's probably pretty simple for you. This is just from t1 to t2, and you can imagine that t1 is 0 and t2 is 1, f of gamma d, which is t plus it squared, multiplied by gamma prime of t, which as you can see is 1 plus I dt. And now we just simplify this like a regular integral. This becomes 0 to 1 t squared multiplied by 1 plus I cubed, if you factor out the factor of 1 plus I. Or like that. Of course, this is a constant, so you take it out. And then this just becomes t cubed over 3 from 0 to 1. And so that just becomes 1/3 multiplied by, what's 1 plus I cubed? Well, it's 1 plus 3I minus 3 plus minus I, which gives you 2I minus 2, or 2/3 times I minus 1. There we go. That's the integral of z squared over this line. As you can see, it gave us a complex result, and it actually didn't even take that long. It was pretty simple. So now, how do we know that this is path independent? Well, it's via, oh my god, a very clever use of the chain rule. You see, remember that every single reparameterization of a curve is equal to that curve composed with some function, let's call it alpha of t, that reaches every single value of t that the original does. So essentially, the original just walks up straightforwardly through t equals 1, 2, 3, 4, 5, and so on. This one takes a very different path. But at the end of the day, since alpha of t is not equal to t most of the time, if it was, then gamma 1 and gamma 2 would be parameterized the exact same way. Most of the time, this takes a much different path to get to each of the t values, but in the end, since it covers all of the t values, it covers all of the points that gamma 1 of t does anyway, and so they end up the same. And you can see this if you try to take the integral with this definition. From t1 to t2, f of gamma 1 of t, gamma 1 prime of t dt, has to be equal to t1 to t2, f of gamma 2 of t, which is gamma 1 alpha of t. Gamma 2 prime of t is just gamma 1 prime alpha of t, alpha prime of t dt. So, one last property of contour integrals is the triangle inequality. In specific, the integral of the absolute value is always less than or equal to the absolute value of the integral. And so, These are a few of the nice properties of the contour integral. Next time, we're going to cover one last big important thing, that what we call path independence. Specifically, when is if gamma 1 and gamma 2 have the same endpoints, but if gamma 1 and gamma 2 have the same endpoints, but are not the same curve, parametrized in two different ways, then when is the integral of f over gamma 1 equal to the integral of f over gamma 2? Now, that's a topic that we'll explore next time. Thank you everyone for watching.